So I currently work with the national testing system in Norway, which is a national monitoring system in the primary and lower secondary school, and there I work with a statistical paradigm called item response theory, which is what I will be talking about today. I work at the Center for Educational Measurement at the University of Oslo, where I'm currently doing my PhD. Um, Item response theory is a statistical framework aimed at measuring something we can't observe. Um, Imagine, for example, we couldn't measure height or length. And how would you measure that? It's if you weren't able to take out whatever, uh, like a measuring stick to measure the height, how would you think of being able to identify the height of a person? It's a bit weird example because we all have high eyes and we can see how high people are, but it makes a good analogy to be able to kind of think of this latent thing, this unobservable thing that we aim to measure with item response theory. So if you want to, you can check out a measurement tool that was developed by some Brazilian or a colleague of mine's friends in Brazil, where you can answer some questions which we call indicators. In psychology, these would often be called items, and in education, we call it tasks, but we use this to get to tap into this latent thing, this underlying construct that we aim to measure, but we can't measure directly. I personally work with measuring students' math skills, and it's kind of hard to cut open their heads and identify it in person or measure it directly. We need a mathematics test or a set of mathematics tests to be able to measure this skill. So by kind of tapping into this underlying construct with indicators, we are able to look at what covaries and extract a measure of the underlying latent skill or trait or construct or factor. It has many names. But I will be talking about three things during this talk. And the first one will be just a general introduction to item response theory. And it will be in no way a complete introduction, but will give you some, the necessary basics. I will follow that up with a hands-on light coding setting. So if you want, you can follow that. But the data isn't available, so I'll publish the data so you can play with it later. And next, I will come to the two main topics of this talk, and that is comparing test results, which is often used if you have two different tests that is given to different types of or different students, and you want to compare the results. It's a bit hard to judge how good a student is that got 23 points on one test compared to a student that got 15 points on another test. But this allows us to do that. But when you compare test results, it's also important that this comparison is fair. And that's what I'm going to finish with. And it's going to be about something called differential item functioning, but more on that later. So what is item response theory? It's a family or a paradigm of a number of different models. There is too many models to name them all here, but these models, they aim to describe the relationship between a person's response on a given item and the underlying trait of the item that is used to measure. So item response theory is also known as latent trait theory, strong through score theory, modern mental test theory, and a bunch of others. And when I talk about underlying trait, as I said, latent variable, an observable variable, construct, factor, it has a bunch of different names because it's used in a bunch of different fields. So in education, it's often proficiency. In Psychology, it would be factor if you come from a factor analysis approach. It can be construct as well, coming from psychology. And yeah, so I apologize for the lack of concise terminology, but be aware that depending on which field you come from, there is a lot of different names being used. So the advantages with IIT, and if you're not familiar with IIT, I assume you're not familiar with the other option of an analytical approach, which is classical test theory. The advantages of IIT is that given that you have enough items, you can get an ability estimate or a trait estimate that is independent of which items you use. So you can use a subset of items and get a concise measure of this underlying trait. It also gives a lot more accurate information or sophisticated information when it comes to errors. So in the other approach, which is classical test theory, which is often looking at test level, in item response theory, where we look at item level data, so we don't summarize it, we look at all items individually, we get a more nuanced error estimate that is conditioned on a latent trait level or our underlying variable. But if we're going to have this independence of which items are used, it's important that you have a rather homogeneous item pool, because you need to have an item pool a pool of items that all tap into the same construct or latent trait. I will try to use item and construct because those are the two words I'm familiar with. If it's too heterogeneous, the ability estimate would have very little meaning because it would be then dependent on which items are being used, in the sense that which part of this underlying thing, this construct, is being tapped into it. So I think that's yes. And then yes, more detailed diagnostic informations, more sophisticated possibilities when it comes to a lot of statistical analysis. I'll mention a few of the different types of advanced models we can use, but in general, you get a lot more flexibility at the cost of higher mathematical complexity and higher computational demands, and unfortunately, higher sample demands as well. And there's quite a few others, and there's some books that I'll refer in the end that you can read up on if you want to learn more about item response theory. So item response theory, as I mentioned, it has terminology from a bunch of different fields, which is because it's used in a bunch of different fields. It's used in education, where I'm at. It's used in psychology, where a lot of my colleagues are at or comes from. You have it in health measurement. For example, how much pain you feel is something that could be measured using indicators. And using sum score, or just a sum score approach, you would get less possibilities to get an accurate estimate, and not you wouldn't get that much information about how accurate your estimate is either, and also how well your indicators work. It's used in market research, it's used in service, it's used in cognitive diagnosis. You can use this to basically get an estimate of a psychological trait. And there are people who use large data from Facebook, for example, that you can use to use as indicators for a latent trait to get an estimate of an underlying psychological trait. For example, political affiliation. Not that that's current in any way or form. But I will focus on education because that's the field I know the best, and this is kind of the core of the topic today. So in education, item response theory is used in some rather well-known and some not that well-known systems. A lot of people have heard about something called PISA. I don't remember the exact what the acronym is for, but these are international large-scale assessments. So they aim at giving information at country level about how the educational system works. They're run by OECD. OECD also have PIAC, which is a similar program to PISA, which also measures the literacy level in the population, but it's aimed at adults. You also have a different organization called IEA. They run something called TIMSS and PEARLS and a lot of other tests. And all of these are aimed at getting information about student proficiencies in a lot of different domains, together with survey data such as socioeconomic backgrounds, motivations, environmental awareness, to mention just one of many constructs that is also included here, and then looking at how the attitudes and knowledge level of the populations are. And in these systems, you have quite a lot of advanced methodology being necessary to be able to do it properly, and item response theory is underlying most of this. You also have it at national level. In Norway, it would be the national tests, or nasjonale prøver, as the Norwegian name is, which I currently work with. But the best known examples, I think, is the American system, where they have a lot of high stake educational tests like the ACT and SAT. They are also based on this IIT approach, but most national testing systems also base themselves on an IIT approach when it comes to the statistical and underlying methodology used. Denmark, for example, there's a lot in the Netherlands and a lot of countries in Eastern Europe, for example, uses this as well. Is there any questions? Then I'll just move on ahead and let's see. And there's a lot of other settings as well. So you have, as I said, a lot of item response theory models. I'm just going to mention them by name and a little bit about their properties. So you have the most common ones being Rush models, which is different but the same from a philosophical standpoint. Due to the underlying trait that is measured, it's measured on a scale that gets interval properties. That means that it gets an increase from -2 to -1 is the same as an increase from 1 to 2, which means measuring differences quite a lot more interesting. And mathematically, the Rush model is only one of these models that does this. And the other models has an approximation to this attribute on scale level, but it's only the Rush models that mathematically does that. But a similar model to the Rush model is something called 2 or 3 parameter logistic models. And both these types of models are used at dichotomous items, binary items, true, false, correct, incorrect items. So if you have a test, for example, a mathematics test, you would use these types of models to analyze it. In psychology, on the other hand, you often have a rating scale. It's where you have, for example, you disagree a lot, or you disagree, or you agree a lot, for example. These are called polytomous items. And the one I just mentioned is an example of a Likert scale approach. And there you have a few models, depending on what kind of data set, you have a few models that are appropriate to use. You have the partial credit models, or generalized version, the graded response model, and the rating scale model. And what they do is they move away from the typical factor analysis approach, where the indicators are assumed to be continuous, but they're not really. So in a factor analysis approach, you assume that the responses, or it's built on an assumption that the indicators get data on as a continuous variable. So the 1, 2, 3, 4 that you will have in your data set actually represent a continuous variable. But it's only an ordinal data, quite frankly, in the sense that 1 is less than 2, which is less than 3, which is less than 4. An example of this is the Likert scale. And if you're from the field of psychology, you will find this example quite familiar. It's often used that we strongly, or one of the types of response scales in a survey or diagnostic form or different types of measurement tools used in psychology is that you strongly agree, disagree, agree, strongly agree. In your data, the difference between each of these responses is the numerical value of 1. But is this distance accurate? It could be that the distance between strongly disagree and the distance between disagree and agree is quite different. You could, for example, ask the question like this, with having 1 being disagree, 2 being somewhat disagree, 3 being somewhat agree, and 4 being agree. And here you see the numerical value between disagree and agree suddenly jump to 3 instead of 1, which you have in A. And you can also have a neutral response. So, see, I have a typo here. So these are quite arbitrary numerical values for our underlying, as the numerical values are arbitrarily chosen. It's logical, but it's quite arbitrary and you could easily change it. And here is one of the places where item response theory can fix this arbitrary aspect. You can also use a bunch of different models, as I said. You have multidimensional models, explanatory models, and too many to mention here, but these are the books that you would be interested in looking up. So, as I said, we're going to focus on the RASH model, the 2PL model, as in the 2-parameter logistical model, and the 3PL model. They all look very similar. They are based on the same equation, pretty much, and with a few restrictions, it's the same. So the theta here is the underlying ability level or proficiency level or the factor level or construct or latent variable, and is used as the x-axis in something we call an item characteristic curve. This curve represents the probability of given a level of ability, you either get a 0 or a 1. So given that you have -4, you would have a rather strong chance of getting a 0 on this item or responding a 0. While if you have a latent trait level of 2, it would be a very strong chance of your response corresponding to a 1. And I remind you that this is binary items. And in this equation, you have 3 types of variables. You have the discrimination of an item, which is proportional to the slope. And this indicates how good an item is to discriminate between different respondents of different trait level. So if you have a strong level of discrimination, the A would be higher and you would have a steeper slope, meaning that it's better at separating respondents at a very specific trait level. The next variable, the D, is the difficulty of an item. This corresponds to where there's a 50% chance of either scoring a 0 or responding a 0 or a 1. And depending on what the G factor is, that means, well, it's between the lower level and it's halfway between the lower level and the upper level, the lower bound and the upper bound. But if you have the guessing parameter restricted to 0, that would be when you have a 50% chance of getting it correct. So as I said, the guessing parameter, if you have a multiple choice item, for example, with 4 options, there would be, given that all the options are similarly, that you don't have a bad option. For example, if you have a picture and which car brand is this, and option A is Ford, Toyota, Volkswagen, and then the option 4 is orange, then that wouldn't really be a good option. But given equally good options, you would get a guessing parameter of maybe 0.25. You can visualize these item characteristics curves in R. We're using the package that I'll use for most things today. And I can show you how that works. Is this large enough when it comes to sharing my RStudio screen?
It's okay for me. If anyone's having difficulties, just say in the chat.
Yeah. So using the mirt package and the shiny package, we can use a function called item plot to get something like this. But this isn't super suitable for sharing on a screen, which is a bit annoying. But if we change the discrimination, the A1, so this would be the discrimination of the first factor in a multidimensional model, but we have here a single dimensional model, so A1 is just A. If we change this value, you see that the item characteristic curves gets less steep when it gets lower, and it can even go to be the other direction if it's an item that measures the opposite of what we are interested in measuring. So the higher the discrimination of the item, the more localized the information we get is as well. So you see here, if you have a high discrimination, it would only really discriminate between people of a latent trait between -1 and 1. People of -2 would get 0 almost assuredly, and same with values under that. And it's not giving a lot of information apart from in the area where the slope is steep. This difficulty parameter is about the location, and you can see if I change the position, and I see that parameterization is opposite. So if I change this, and then B is the same, it's the difficulty. It's a bit weird notation here, but if it becomes a harder item, the item characteristic curve, it shifts to the right. If it becomes an easier item, it shifts to the left. And then we have this guessing parameter. So in the example of 4 options, the item characteristic curve would look like this. So regardless of your trait level, you would not be able, or you would always have a 25% chance of getting the item correct. But then the difficulty of the item is halfway between this lower bound and the upper bound, and then it's about where you have about 0.62% chance, or a 62% chance to get the item correct. It's also a fourth parameter model where you can play with the upper bound in this shiny application, but that's very rarely used in any analysis that I'm familiar with. So moving back to the presentation, these item characteristic curves is created by this function, which is called an item response function, which is influenced then by the discrimination of an item, difficulty of an item, and the guessing parameter of an item. In a 2-parameter model, instead of the 3-parameter model, the guessing parameter is restricted to be 0. That means that we have this situation, which is used as an example here. And these models are quite a lot more stable, which is one of the reasons they are used quite a lot more frequent, despite items being used on multiple choice. So I'll be using the 2PL, or the 2-parameter model today in examples, but I also mentioned the Rush model, which is a 1-parameter model, and there the discrimination of an item is restricted to be 1. So then you only have the difficulty of the item left as a parameter. So you have the Rush model, which is a 1-parameter logistic model. You have the 2PL model that uses discrimination and difficulty. And you have the 3-parameter, which uses discrimination, difficulty, and guessing. So with these functions in mind, I kind of want to do a little bit of a hands-on approach and show you guys how we can model something without directly observing it. So using the height questionnaire that you could see earlier, it's still available down in the corner if you want to have a look at it. We're going to try to measure the height of people who have responded to this survey by not really measuring their height, but measuring their response to a questionnaire. So in the data set we have available, it's 252 complete observations. it's important to note that these are self-reported heights, and it's used 14 dichotomous items. Regarding cutoffs for the steepness of an acceptable A parameter, it depends on what you have available in your item pool. Sometimes you don't really have any better options, but it also depends on where your information where you want to have your information. So it depends on a lot of factors, but in general, the higher your discrimination is, the better. And then you can have instead multiple items of different difficulty to make sure that you have information spread out over the entire ability distribution. So jumping back into R, since this is after all a user setting, closing this, we have a unidimensional approach, which is what we're going to play with here. Going to play with my data, and then I have what was the name of that one? Just killing NAs. And since we're in Norway, I have to use CSV2 instead of CSV, because we use a comma instead of a dot to indicate decimals. And then we have our height data. So this data looks like this, where you have a bunch of, or 14 items to be precise. We have an ID, we have the true height, which is what we're going to play with later. And then each of these items corresponds to the items in the questionnaire, which we're going to have a little bit of a look at afterwards to see how well these items function as indicators of height. So it's a bit important that the data has a specific structure when we run an analysis using mirt, which is my preferred IT package in R. So my data IIT, we need to only have the binary options here. So that would be item 1 to 14. We don't want to include the 2 first columns. And then let's see, we have see like that, and then we only have our binary options.
So we have another question asking, why do you prefer mirt?
So there's some different tools available. You have TAM and you have LLTM. LLTM, as I'm aware, it's not being updated as frequently. TAM is a good option, and I wouldn't say you shouldn't use that, but mirt has a lot of options for multidimensional analysis and have a lot of good estimation techniques that are implemented. The developer is very responsive, and it has just an incredible array of features. It's also slightly influenced that my PhD supervisor uses mirt, so I'm a bit biased there. But in general, it offers me almost all the things I want from an IT software while still being very user-friendly. And the only weakness I would say is within the plotting. So mirt is doing quite amazing on everything apart from plotting, if that answers your question.
So Erica, if you've got any follow-up question, I've unmuted you.
Yeah, no, sure, thanks. Yeah, I think I only encountered some problems with some, or not problems, but missing fit indices only. But that was my only problem with mirt so far.
Yeah, so fit indices is a bit hairy to get out if you have missing data. But having the M2 function in mirt, you can get a lot of the fit indices you want out. But it is problematic with missing data, and you might want to look at testlet level instead of looking only at or looking at the complete level, which is not ideal. I'm not familiar with the fit indices available in TAM and LLTM, so I can't really compare it with that, unfortunately. So estimating our model is surprisingly easy. With commercial software, it's usually quite a lot of specification. In mirt, it's as simple as this. And I hate it when my instructor says it's simple, because it's simple for people who know what they're doing, but I would argue it's actually not that bad. So I have first loaded my data, then I'm loading my factor structure. So here it's basically unidimensional model. If I increased it to 2, it would quickly be an exploratory IIT model. But when you do a single factor approach, it's a standard unidimensional model. And then we want to have a item type specified, because we're going to play with that later. And we're going to start off with a rush model, and there's our model estimated. But estimating a model is just the first step. We still want to diagnose it quite heavily. I really like how that's quite available to just play with syntax to do that instead of being stuck with reading a 100-page report, which a software such as, for example, Excalibur would do. But first we can start with inspecting it at item level. So for example, if I do like this, so running it across these different, all the different items, we can have a item plot being generated. Just gonna avoid using function names. So we can use the item fit function where we use my model. And for example, so this is what we do here. I'll explain it more in detail when we see the plots, but we group the respondents after the latent trait level to see how the data fits with the model. So let's do 15, for example. I'm doing 15 because that's what's used in the example code. You can use 11, you can use a lot of different numbers, but it's useless with too many groups and it's useless with too few groups. So try to get something that gives you a good amount of respondents in each group. Empirical plot. So we want to plot item I. We want to have our confidence interval to be 95%, for example, and our method to be maximum likelihood. So if we do like that instead. Oh, and we also need to print our plots. So let's run that again. So here we can see how our data corresponds with the item characteristic curves, of our data. So starting at item 1, this was the item that is, are you cold on your feet when you sleep? It's not the best indicator and it's a horrible misfit, but it should be noted that the sample size is quite small here. 250 for a rush model is sufficient for stable item parameters, but not, well, more is better in an IIT setting, and you don't necessarily need more than 200-300, but I would prefer 500 or more when you do an IIT analysis. If you look at the next one, still not great, better fitting, and you can see the items quite well corresponds to the item characteristic curves within measurement or within the area of measurement. Some weird outliers here. But in general, it's not a bad fitting model. So how does that correspond to the latent height that we actually have in this survey? So, the observed height. If we calculate the latent score, you can use that. You can do that using the F-scores function in mirt. Then you get out a list of all the latent variables. You can combine that with, I also want to do the sum scores to show you that it's not always ideal. Oops. Let's see. And combine these together. Let's see, data frame, and then have my data, my data IT2. If you have that together with the sum score and latent height, you have now difference measures. This looks a bit off. Oh yes, of course. My data is the one we should use, not my IT data. Whoops. Now we have a data frame consisting of the self-reported height, the sum score of the survey, and the latent height. And we can, for example, plot these on each other. So we can have the height measures and the true height. Let's use that as the x-axis. And then the latent height. We get a rather strong correlation. It's not an ideal measure. It has measurement error, which is the curse of all latent variable modeling, but it gives us a good idea. We can also use the sum score. Still pretty close, or quite similar. And then we can check the correlation of, let's see. Of our measures. So using our latent height, this would then be a correlation through height and latent height, and this would be with a sum score. And we get rather similar numbers. One of the reasons here is that this is a survey that has been developed and gone through a few screenings, and the items in general are good measures. We can change the measure here to a 2PL model, and you can see how it all looks then. Oops. Not the maximum likelihood, apologies. And we can redo this. You get a slight increase, but you don't get a huge increase. Sum scores in general is a good indication, but there are some problems with sum scores. And I'll show you a thought experiment to illustrate my point. So if you have 7 items measuring something, and student A gets 1 point, student B 3, student C 5, and student D 7. And then we just remove item 5 and 6. Suddenly you have a change in the sum score that would screw up how the sum score works. But with IIT, we don't have this problem, especially if we have a large enough item pool. This example does not have a large enough item pool, just to underline that. But that means that it gets independent of the items. So if you have an IoT approach here, you would be able to bypass this item dependencies. But when you have a well-developed test measuring at different levels quite well, then that's not necessarily a problem. It becomes a problem when you have in a test development process, but also when you want to do more advanced stuff with your test. A classical test theory approach does not really function that well. But one of the ways to illustrate this is also with something called a right map, where you can look at the item difficulty spread together with a histogram of the respondents. Let's see.
Yeah, we have a question. How many items would you need, like, if this is not enough?
It depends on the type of item. If you have a like or a polytomous item with Likert scale responses, for example, you need fewer. I prefer a lot of items because I want to get a measurement error down. So 50 items, 100 items is my ideal setting. But if you can't have that many, to be honest, I'm not sure how many items you should have to bypass this condition. But it would be the more items, the better. And it depends on your error of measurement desire. So you'll need to kind of look that up to match it with how accurate you want your measures to be. If you want a very accurate measure, you need to have a large item pool and reduce the dependencies. If you don't have the need for that high degree of accuracy, it's not that important. So I hate, or when I started in educational research, I really hated the response I got from basically every question, and that was, it depends. But it kind of grew on me, and yeah, it depends. It depends on a lot of things, so I can't give you like, this is the correct answer. Sorry. But yeah, no, wait, that's not what I'm jumping out of. But so yeah.
We have another question too. Can you get feedback from mirt on how some item might not be adapted to measure your construct?
So you can look at that in a bunch of different ways. You can look at it from a typical factor analysis approach, where we look at the factor loading of our item. So if you do a summary of a model, it's, well, item 1 really didn't work. And if you look at that in comparison with the item characteristic curve we got, you can also see that it has a very flat discrimination. So now this was the 2PL. I looked through these pictures before, and in the Rush model, it's restricted to have the same discrimination. But if you look at it in a 2PL, you'll see that the factor loading, while not the same as the discrimination, they are quite highly correlated. And this item, for example, doesn't really do anything for our measure. As you can see, it's like if you have a low or high latent rate, having cold feet when you sleep doesn't really affect how high you are. But as you can see from these other items, it's steeper and steeper, especially item 7 is very good indicator, but this also depends on where I'm interested in getting information. So while it's a very good indicator at this area of the latent rate, it's very bad around here because none of the people around here would answer anything else than 0, and none of the people over here would answer anything else than 1. So it's a few things that you want to take into account, but
any follow-up questions to that, Owen?
But I'll give you a brief look at, just in case it wasn't shown by the questionnaire. But item 7 is Are you capable of getting objects from the top cabinet without using a ladder? So yeah, that sounds like a rather good indicator of height. Am I usually uncomfortable inside automobiles? This can be tapping into a lot of different constructs. Same with impressiveness as a police officer. I especially like the short duvet scenario, but yeah, all of these items to a different extent tap into our decide construct. I think you also have the item 10, if I don't remember correctly. It's a good indicator, and that is you adjust your car seat backwards. So it's a combination of empirical and textual or conceptual evaluations that you should look into when looking at how well an item measures your construct. It's not only statistics, but in this case, it gives you a very good indicator. In mirt, you can also get out these discriminations and difficulties quite easily. You can get coefficients out by using a coef function in mirt. It can be a bit annoying in the start if you forget some things. So we want to do it on my model, and I'll show you how that looks. If you only run it like this, you get it out as a data frame or as a list, I guess this is, and then it can be rather annoying to work with. So we want to add an argument called simplified, where it comes, oops, not that. Should have come out in a list here. It also helps to spell the argument correctly, otherwise it doesn't do anything. But mirt has one caveat, one element that can be a surprise if you're not familiar with it, and that is it uses a reverse parameterization due to the creator being a statistician. So you also need to use the IIT parse equal true. To get out the accurate item parameters. So you can see here that item 7, as we talked about, has a very high discrimination ability. Same with item 10. Item 14 was also quite good. Item 1 is horrible and you should throw it out at once. The difficulty, item 8, for example, is a rather difficult item. It was, do you duck when going through a door? That sounds like something very tall people would do, but not short people. So that becomes more applicable there. So there's a logic to it, luckily. And if there's some logical inconsistencies, I would look at the items and not only look at the statistics, think of them in tandem. To be able to look at how your items spread out over the latent scale, you could look at the B variable here, and it looks quite diverse here, but there's also a package called rightmap that is quite nice. It's not the ideal rightmap generator. It's named after a guy called Benjamin Wright, who did a lot of original research into item response theory, especially the Rush model, which a rightmap is tailored towards. But it is a decent rightmap map that is easy to implement. So just going to have a sip of water. A rightmap requires a few things. It requires the latent trait level of your respondent. So that would be the latent height, in our case, this one. and it requires our item estimates, item parameters estimates. So we want items, and we want our second column here. So running this gives us this right map, which if we drag it a little bit more, is already quite informative. You can see it spreads out quite neatly. Item 8, as we saw, was really hard. But unfortunately, a right map doesn't really tell us about items that doesn't function well from a point of discrimination. So item 1 is considered really hard because it was just a flat slope pointing upwards, but still, still flat, but pointing upwards. So it would be very hard. But yeah, so it has its benefits to illustrate how well you're measuring different levels of your scale, in the sense of there being items spread out over your entire scale. But it unfortunately don't give you a lot more information than that. So it depends on who you're going to present this to. This can be a good communication channel or communication method. Let's see. I think that was what I wanted to talk about when it comes to a unidimensional model. Yeah, you have a lot of other information things from the plot function when you combine it with mirt. So we can have my model and, for example, trace. Nope, that was not the correct one. Type equal to trace. Here you can see the item characteristic curves of all the items. We are now working with a model that was estimated from a 2-parameter logistic model. And here you can see the item characteristic curves for each model, item response functions. You can also get out individual ones. You can look at information. This is, there's a way to calculate how much information an item gives you, depending on the discriminations. I'll stay away from the mathematical formulas right now, mostly because I don't have them. But you can see here from the 2 plots, if we go back here, item 7 had a really high discrimination, as you remember, and it gives you really high information as well, but it's very localized. Item 2, on the other hand, has not that much information, but it's more spread out. And you can see item 6, 7, 12, 14, 10, and 5 is the main contributors to information in this measurement tool. But if you would reduce your item pool here, I would maybe go from them, but it also depends on if you're measuring along the entire latent continuum or difficulty spectrum or what you want to phrase it as. We can see, we can do, we can remove this facet function and look at them all in together. And here you can see item 7, again, peaking up. It doesn't spread out as much as the other ones. And you can see the ones that are highly discriminating are quite localized in the center. But still, I would highly recommend keeping items showing that good information or that high discrimination, as you get a lot more information from them. In a lot of settings where you link test together, for example, which I'll talk about later, the items with the higher discrimination provides you higher statistical power as well, which is a nice feature. But yeah, there's a look. We can also look at test level. That was the wrong one. And here you can see the total combined test information. It's surprisingly easy to calculate. It's a summation of all these item information, or all the item. If you summarize all the item information, you end up with the test information. But then you can see where the test is measuring and giving you accurate information, you can combine this with a SE command. We also get the standard error of measurement. And I mentioned earlier that you get conditional standard error of measurement. And this would be your standard error of measurement conditioned on your latent variable. So you can see this measurement tool is great around -0.5 to 2 on this latent continuum, but it's not really accurate at any other levels. But then I'll give you a quick primer now on item response theory, and I was thinking we take a 10-minute break, and then we'll jump into comparing tests and looking at how we can make that comparison useful. Does that sound good?
Yep, that's fine by me.
Yeah. Unmute myself. But there's some requirements when you use item response theory. You need a decent sample size. You need computational power. Unfortunately, it's a nightmare to do this by hand, and I don't know anyone or no one I know has tried. But the more complex model you want to use, the higher the sample you need. For a Rasch model, you get stable item parameters around 100 respondents, but you get 200 to be pleased, to be honest. 2PL, 2 to 500, 3PL, 500 or more is my rule of thumb. There are some research about stable item parameters out there that you can look up if you're looking at small sample application of item response theory. It's also a few assumptions underlying here, and that is that we have only one single construct being measured if you don't use multidimensional models. That you have something called local independence, which means that you don't have, if you control for the underlying latent trait that we measure, there shouldn't be any leftover association between the items and or between the different items in the test you're analyzing. And you also need to have a correct type of a response function. But apart from that, well, these can usually, with a well-developed test, they usually hold. It also builds on oftentimes builds on a normal distribution of the latent trait, but there are ways to bypass that as well. So how do we compare tests when we have different tests? If you have test A and test B, and some people take test A and some people take test B, how do you see this results in comparison? You have a few different types of linking: equating, vertical scaling, concordance, projection, and statistical moderation, but I'll focus on the top two here. Equating is when you want to draw the same inferences about the same construct, about the same population, in the same measurement characteristic. That basically means if you have the same population and you have two different test forms that are aimed at measuring the same things. In vertical scaling, it's similar with the construct and measurement characteristics, but dissimilar in population, meaning that you have, for example, students in grade 3, 4, and 5 taking different tests that you want to connect together, which you then would have a scaling situation where you want to develop a scale across multiple grades, which is what I currently work with. But to do this, there's quite a few methods that all relies on something shared. I'm going to show you something called concurrent calibration, which is a rather straightforward and easily implemented solution, but you have something called a mean-mean transformation. So if you have a test equating setting and you have two different tests, you can shift the latent continuum by the difference in mean between the two groups. If you do something called a mean sigma equating, then you have you don't only shift it by the mean value, you also stretch the underlying scales proportional to the variance of the standard deviation of the scales. But you lose a lot of diagnostic possibilities when you take these approaches. You also have some nonlinear transformations, but I will not go into them. But if you have a setting where some students take multiple tests or some items being shared between the test forms, you have something that can connect these things together. And this makes it possible to look at it all in relation. And a typical implementation here is that you have different types of test forms. So for example, if you have item blocks, so groups of items, group A through G, and then one test form is block A and B, one is B and C, one is C and D, and so on. This can either be in a test equating scenario where these would just be different groups within the same population, or it can be in a grade scenario where these items in item block B is suitable for 3rd and 4th grade. Items in item block C is decent for or suitable for 4th and 5th grade, and so on. The other approach is something called equivalent group design. So you might want to split your population into multiple groups. It looks similar to the common item design, and a lot of these designs combine different features, but you could rely on, for example, the assumption that if you split your group into 2 groups, they should have the same mean ability and distribution, or mean and distribution of ability, and then link that way. But if you share something between them as well, you get an even stronger link. And you have something called, this wasn't supposed to be grayed out, anchor test or a scale test design. We have here in this scenario, you have one test that all students from grade 3, or one group of items that all students in group from grade 3 to 8 takes, and then some items that are tailored to the different groups. If you do it within one group, this would then be an anchor test. So for example, this would be year 3, or this would be 2013, 2014, 2015. And you don't really need to have this link between them either. You can only have item block A in 2013 and item block B in 2014 and so on. And then you would have some items shared throughout the years that would be kept stable. This is the method used in the Norwegian setting, and combined with, well, it's almost the setting used in a Norwegian national test setting. But
so question about the minimum sample size for each item block.
Definitely not less than 5, I would say. You have a lot of analysis or simulation studies that are done when it comes to looking at connecting tests together, and this is mostly in the thing we'll talk about in the next segment about looking at fair comparisons. But you need enough shared for there to be a you need enough shared for there to be enough items to both represent the construct you're measuring. So many construct, you need to sample your construct properly in this anchor or this shared item, common item pool. So it depends on how complex your construct is, and it depends on the types of items. But
there's a further question. Should they have the same sample size? I mean, if you've got unequal sample sizes between the item blocks, do you have to handle that differently?
Not necessarily. Or sample size in the sense of items, or in the sense of test takers?
I'm not quite sure. I can unmute you if you want. Sorry. Sorry, you just unmuted yourself and I pressed mute again, sorry.
Oh, it's okay. I was referring to the number of test takers or responses for each item block.
Yeah.
So because we are actually splitting up or stratifying the item blocks, right? So I was thinking like what, and usually if you look at this, it's usually implemented on a large scale with different students for each year level, and maybe for different year levels even, or years. across time? I'm not sure if time could change for each year level. So
if you, it
there might
depends
be.
on the respondents to the item. So you want to have a minimum number of respondents, similar to if you want to analyze a single test, you need at least 200 to get stable parameters, and you need around 200 to get stable parameters on the items in each block as well. The higher sample, the more stable item parameters you get, or more accurate or smaller errors. But I would recommend at least 200 on each item. So that means 200 on each item block.
Oh, okay. But does it matter if, for instance, in this diagram that you're sharing for anchor tests or scale tests, you have a split for A, B for your level 3, and then for level 4, you have the same B. Does the B item block have to be coming from the same sample size?
It does
Even though
not
if they're
have to have
coming
the
from...
same sample size, but I
Okay.
would recommend having at least 200 in each, so that you get
Mm-hmm.
the ability to do diagnostics as well. Because you want to see that, for example, you don't have, or you want to investigate your measurement invariance for these items, just make sure they measure the same, or that they behave the same in each grade, and you need a certain amount of statistical power to be able to do that. So I would
Okay.
recommend having not groups less than a couple of hundred, but it's not ideal settings always, but you'll get very large error margins if you have less than that.
Mm-hmm. Okay, thank you. Thank you.
Yeah, cool. I'll show you in practice how you implement this using R with the project that I'm currently working on, which is the national testing system. And we implemented in 2018 a similar design as the equivalent group design with common items, meaning that we split. I'll take you from the start on the Norwegian test just briefly. The 5th grade test is taken by all students. The 8th grade test is taken by all students. What we did was split the 5th grade test into 2 blocks of items that were quite similar, and similar with the 8th grade test. Although the group 2 of the grade 5 items were slightly harder than group 1, and group 8 was slightly easier. The group 1 in the 8th grade was slightly easier than the group 2 in the 8th grade. So what we did was we constructed one test that consisted of these 2 items groups, the 5th grade group 2 and the 8th grade group 1, which we call the linking test. So we had half the students we recruited in 6th grade take the normal 5th grade test, and half the students in grade 6 take the linking test. And then in grade 7, we had half the students take the linking test and half the students take the 8th grade test, so that we got a decent sample across the different test forms, and in addition, build in a safeguard in case some items really didn't work. For example, 8th grade items didn't work on 6th grade. We still had a proper link throughout the years. So this extended data collection was then aimed to connect grade 5 and grade 8 to put these 2 test forms, grade 5 and grade 8 test forms, on the same scale. The data structure of the test what I will do right now is we have one group, essentially. We have 6th grade. So it's a normal distribution assumption for one group. It's 2 test forms and 3 item blocks. So national test for grade 5, group 2 consists of 23 items and was shared between the 2 item blocks. And then let's jump back into mirt. Let's see. So then we have a comparison setting. Let's see, just getting my notes in order. Cleaning a little bit. And again, you're going to use, or I'm going to use mirt because, as I said, I really like that function, that package. We're going to use tidyverse a little bit because it's practical, and also ggplot. And then we need some data. I have them stored as grade 6 national test. There we go, and the linking test data.
So we have another question,
Yes.
which is, what do you mean by quite similar items in the blocks, and how did you evaluate the similarity?
So that means that we had similar content representation. So a construct is never truly unidimensional. It's more complex than that, and in this case, it's the numeracy tests that I maybe forgot to mention. So that means we had equal representation of statistics, algebra, and measurement and geometry, which was the 3 different domains, or numbers and algebra. So we had the same, like they were quite similar in the sense of content, and the only thing that we tried to have different was a slightly higher difficulty of these items, due to the fact that we was going to administer the 5th grade items to 6th and 7th grade. We wanted to avoid the test being too easy. It's essentially like a Form A versus a Form B of a test, just that Form B was slightly harder. So as similar as we could. And then similar for 8th grade, one of the form, we took the slightly easier items because we were going to give them to younger students, and we didn't want to give them items that they had no chance of getting correct. Felt kind of wrong to give 6th graders or give 6th grade students hard 8th grade items. Does that answer the question?
I think so. I can unmute you if you want to follow up.
You can evaluate the similarity. I didn't respond to that. Using, for example, a bifactor model. I don't think we'll have time for it here, but you can use a bifactor model by looking at I'll get to it after this code clip, how a bifactor model works, and then I'll pick up the question if that's okay. So we want to merge our 2 data sets to make our job easier, because it's a concurrent calibration. So we basically throw everything into the same model. We also want to make a group variable just to have that for later. Let's see, so then we make one group variable, which is group 1, and then we replicate that across, or a number of time equal to the number of test takers in the first data set. And then we have a similar group for whoops, 1, 2, and there we go. So you can see from this that we have, oh, this was quite messy. Just gonna clean up quickly here. So I have 899 students taking the first test and 819 students taking the second test. And then we have a combination here, 1,718 of the total items. As I said, 23 was shared. So we can specify again our model. Where we have use just a normal unidimensional model using my data. We again want a unidimensional model. That's why we have the 1 item type. The 2PL model is what was used in the, or is what is used in the national tests, and that's what we used in this setting. And we want to have, yeah, that's about it. And again, if you look at this data, you'll see the, whoops. I forgot to remove the first values here, because those are IDs and gender values. And like that, and then and like that. And now we have only item data. Inspecting the data, we can see that this always happens when I don't inspect my data. Just super quick, gotta do something. If we inspect the data, we can see that we have a number of missing here. In some items, there are nothing missing, and with some items, there's 819 missing, and with some items, there's 899 missing. That corresponds to overlap between the test forms. So if we specify our model, as you can see, mirt works quite quickly when there's a small sample size. And by small, I mean we don't use the 60,000, but the 700. Then we can look at, we can get out the student score. Using the same function we used earlier for the latent height. And then we have the model, my model. We can get the sum score to show you how the sum score differs. Student sum score. And then we use the apply function because it's quite neat. Sum, and then we want to ignore NAs. Like that, and you can see that both of these are equal lengths. And we want to merge all of that together with the group variable. In a data frame. And then we want to add then the, let's see, just so I get this correctly. Group, our student IT score, and our student sum score. Like that. And then we can plot that using our ggplot command. And there we want to do the test comparison as our data set. Our aesthetics is the X value is the, it's called F1, as you'll see when I show you the column names. And the reason for that is it's score on factor 1. As we use the unidimensional model, it's F1. Then it's the Y axis as the student sum score. And we also want to do a color for grouping. Like that. And we want to use the jump point, I think, here to generate this plot. And using a 2PL model, you don't have a one-to-one correspondence. So you can see here how the different tests are quite different, but there's some overlap. But if we use the Rush model here, we get out the one-to-one correspondence, and you can see exactly how much, for example, 20 points on the test, on test for the group 1 corresponds to 15 points on the test that the other test took. So it's quite a large difference in the latent ability of students, or in the scores that students would get on these tests, or students with similar points on the 2 tests have quite a big difference as well. This actually corresponds to about a year's worth of growth. So you should be careful when reporting this to school leaders. You want to also look at the fit between these things. But we can steal a little bit of code from the previous script. And then we want to do the my data. And like that. I'll stop this in a little bit because it takes a little bit of time for these plots to generate, but then you see how these plots work for the different items. This is a very typical diagnostic approach when you work with item response theory. If you want to do a dimensionality assessment, there's a bunch of things we can do. We can do a parallel analysis, but it requires some modification due to it being binary data. So you want to use a tetrachoric correlation matrix instead of a Pearson's correlation matrix. But you can also use a multidimensional approach. So if you use a bifactor model, and taking up Erica's questions from earlier, how to investigate if they are the same, you can, for example, have the questions or the items from one group be one subfactor and another test form be another subfactor. And if these are basically negligent amount of variance being explained by these factors, then you have a very homogeneous or very similar test forms. This is what we did when we looked at the comparableness in the linking test, for example, to see if these tests are similar, which they turned out to be, luckily. And with these multidimensional models, you have a lot of other structures you can use as well. You can use a correlated simple structure, essentially estimating one IT model out of each of them and looking at the correlation. And that's also an approach that would be suitable here. But the last topic I wanted to talk about is going to go rather quick. It's about test fairness, which is also something you need to take into account when looking at combining tests. So this is called in technical or in IT language, it's called differential item functioning, and essentially it's a setting where items function differently. So when you're used to it, it's a rather self-explanatory concept. So if an item behaves differently, it tests differently, and that can lead to quite unfair interpretations of the results. So I have already run the analysis, so it shouldn't take too much time. But the essence here is that we run an analysis where we identify, is it this one? Yes. So I'm not going to go through this code, it's just to illustrate the way of the analysis. You run first a constraint model where all items are considered equal. Then you run a bunch of models where you under-constrain one item at a time, meaning that you can see, you let each item be estimated uniquely per group. And then you can run a likelihood ratio test to see if this difference is significant. You will end up with a set of items that are not showing differential item functioning. So then you have like a purified group. Picking the items with the highest discrimination there will give you, so the 5, for example, highest discriminating items will give you an anchor you can use to connect the test together. That will not be at risk of having a contaminated link. Normally, people don't take these great steps to check it out, but I would argue they should. And if you run this last model with an anchor of some items, you can look at the rest of the items. And these items, as you can see here, they show some difference. For example, this one is quite substantial difference. It's both has a lower discrimination in group 1, which is the focus group. Group 2 is a reference group. So here you can see that this test does not behave properly in both tests and should be allowed to, or it shouldn't be forced to be considered the same item in both test settings. The rest of these items are, it looks different, but quite similar, to be honest. And a normal rule of thumb is that if there's a difficulty discrepancy of 1.5 or about a half of a logit, then you shouldn't let it be considered the same. There's not a lot of research on this from a conceptual construct point of view, but from a test fairness point of view, there's also a way to evaluate the impact of that I'll show you later. But most of these items functioned quite well. This one wasn't that great. And there's also one that was quite horrible. This one. So this one measures very bad in the focus, in the group we had as a focus here in this analysis. And if you let these items be, yeah, this is the method that I just briefly skimmed through, but there's a bunch of other methods. And I skipped over that. But if you let these items be estimated freely, you avoid a situation where you have unfair comparisons between students. The consequence can be, as you see to the right, it was the Norwegian mathematics exams a few years ago, and just around the cut points of where there was a pass-fail setting, girls had almost a full point. Girls of the same ability as boys almost got a full point more, which can be quite detrimental in a pass-fail setting. So that's something that can be quite problematic if not taken into account. You can also use this, for example, on a math test if it's a language-based math test or it has items with language in it. It can be used to disenfranchise minorities that don't get to show what they know in mathematics because they stop by reading. And then you have a differential item functioning that is which is then caused by a misunderstanding or inability to kind of get to show what you know of the targeted construct because some things are keeping you back. But these things can be sorted out with two approaches. I personally like number 2. You can ignore the items. It's the easy one, or you can allow the items to be estimated freely across groups.
So another question.
Yes?
The ICCs you showed on the plots were from separate calibrations or not?
They were for the same calibration using 5 of the items as anchors that had been identified as not having diff. So we had a purified anchor connecting them, and you have quite good statistical power using 5 items. So it was the same calibration.
Okay.
Yeah, and that's about it for me. There's some books you can check out that are available online if you have the DOI number and know where to look. Modern Psychometrics with R is a bit of a jump into on the deep end, and using R for item response theory and model application is a bit more gentle approach. And if you want to learn more about the project we ran, there's a link, or the QR code is for the report that we had, but that one is in Norwegian, unfortunately. So thank you.
So any further questions? And I don't have a question so much as an observation with your package you were using and its interactive shiny thing that's automatically implemented. I've never seen that before. That's pretty cool.
Yeah, it's nice in a teaching setting. It's more fun when other people get to play with it because then you get a more intuition on the.
Yeah, I can see that being a nice, gentle intro if you're working in education and maybe you're not a programmer.
Yeah, and the key to getting item response theory is understanding the item characteristic curves, to be honest.
So, further questions?
I think we'll call it then, and thanks for coming.
Yep, and do consider joining in to contribute a lightning talk.
Yes, please check out next meetup
Or,
if you want to contribute.
someone into contributing if you know someone who's good.
One of the focuses.
I mean, convincing.
Yeah, one of the focuses of both USAR and ALE is inclusiveness, and we really appreciate people of well, not people like me. So white males are not, well, we're encouraged to join as well, but everyone else is even more encouraged, is a diplomatic way of saying it. And it will probably not be a hybrid solution due to the current situation. And that means if you want to contribute from somewhere else in Oslo, feel free to do so. So thanks.